Alright, good afternoon. Today we are going to go over working on some example for displacement analysis where we have we covered the standard form of displacement analysis for some standard form of mechanism. So now we are ready to look at some examples. After covering these examples, you should be able to do displacement analysis for any kind of mechanism. Yes?
Do you know when our exam is going to be?
Most likely October 24th.
24th.
The first. So, just stop me if you have any question while we are working on the example. So I will start with the first one. We are doing the examples as a class activity, so then you have the better understanding about how you should approach those classes. So here we have this mechanism. This is one slider, and one link it has been connected to this slider. Another slider is up there, which has been connected by this joint to that link. So for this mechanism, label the links, joints, and the angles, and calculate the degree of freedom. Makes sense what I'm asking you. Yes.
There are both sliders?
Yes, these two are the sliders, and there is a rod connecting these two. So when you move this one to you go to that side. Number 5. How many links can you see here? Pardon? 2? What are those 2 links? You said 2 links. How did you count them?
We have 4 links. First one is brown.
One is brown.
And then we have 2 sliders.
Number 2, number 3,
And the link is blue.
and this is number 4. Number 13. Label the joints. Would you come to the board and label the joints? Whatever you can, yes. Just one circle around that. Okay. That's it.
There's two.
Yes. Because one is this rotational between link 2 and link 4. The other one is translational between ground as one link and slider as another link. So, thank you. So we have 4 joints and all 1 degree of freedom, 2 rotational, 2 translational. 1, 2, 3, and 4. The first, yeah, said 2, then someone else said 4. So M is gonna be 4, 1 link, 2 links, 3 and 4.
So, I just want to ask, for the 4 joints, there are 4?
4 F1, 1 degree of freedom. 1 is this pin, which is rotational. This is another pin right here. So 2. Between the ground and the slider, they can move with relative together. So it's kind of translational. So another joint here between ground, which is 1 link, and this is slider. We should count 1 more joint, and we count ground once. This is ground, but we count once. All right. Now, if this is O, I can form the vectors. For this one, I put the arrow here, starting from the origin. Put the arrow right there. And for this link, I put the arrow at point B. Or you can put the arrow at point A. Vector loop. Point B is the point with 2 arrows ending to that. So try to reach the point B. OB equals to OA plus AB. So the way that I form the vector, it's gonna tell me for this link, I should measure the angle at this end. Theta, let's call this 3 theta and 4 as a slider. So theta 3 is representing the angle of this link with the ground. There is no need, we don't have any other angle to be defined. If this length is A, this length is B. A from here to here, B from here to here, and this length is C. So constants A is not constant, B is not constant, C is constant, and that's it. Theta 3 is changing. So variables, whatever is moving is changing when the mechanism is moving should be considered as a variable. A, B, theta 3. So the nouns would be constants plus degree of freedom for 4 links and 4 joint degree of freedom would be 3 times 4 minus 1 minus 2 times 4, 1. Theta 2, suppose A is given, I assume A is given, we are solving for B and theta 3, but you might be given by B or you might be given by theta 3 and you should solve for the other two. one of the variables should be null. We are solving for theta 3 and b. Alright. By looking at this vector loop in x components, I can write OB. O from O to B doesn't have any x component, so it's going to be 0. 0 would be left side, doesn't have any x component, or you can write B cosine of 90. B cosine of 90 equals to A cosine of 0 plus C cosine of theta 2. B sine of 90, A sine of 0 plus C sine of theta 2. Simplify this, B cosine of 0 is going to be 0. A cosine of 0 is A times 1 plus C cosine of theta 3. This one is going to be B equals to A sine of 0 is going to be 0. C sine of theta 3. Two equations, the unknowns are theta 3 and A. First, I can get rid of theta 3. If I square this side, add them up, c square cosine square, c square sine square is going to be c square, negative a square is going to be positive, a square we are looking for b, so b square will be c square minus a square and square root. B is going to be this. It's a triangle with the angle of 90. We could say that before we derive this, but I just did a step by step, and you should do the same things because you don't get lost and you don't miss any. Yes.
Will this only be one node? Because B can also be in the.
B cannot be negative, yes. B cannot be.
What if we allow for it to like go under?
I mean, for this one, I assume it's going to be this, but if you want to look at the negative side, then B is going the other way. So it's going to be something like this. If B is negative, B is going to go in this direction.
Yes.
If you like, you can consider that mode as well. So theta 3, back to this equation, cosine of theta 3 will be negative a divided by c, sine of theta 3 is b divided by c. Two angles from here, two angles from sine equation, find the matching. Alright, this is the next. We started with the easy one, so we go to the more advanced mechanics. Again, make sure that you are following the steps that we should do to solve this type of the mechanism. One of the homework problem, and in the exam you might see something like this. To O4 point A, point P. So first, find the degree of freedom. So as a class activity, first find the degree of freedom for this, then we can continue on the next step. This is what you need to do for any kind of mechanism. Find degree of freedom. I don't see it how. Number 5. It's your lucky day. How many links can you see? 4. N equals to 4. One is ground. What will be the second one? O to A. A to B, okay. B to C. 4. Okay. Number 8. Number of links are 6. How many joints can you see there? 3, you said? And no joint between degrees of freedom? So should I put 0 here? Okay, 630. One more. Ryan. He's not? Number 27. Charles. Yes. How many links can you see there? 4. Okay. And joints? And all, I know 0 digraph. I mean, number 19.
I don't know. I'm assuming 7 links.
7 links. How many joints? How many links? 7, you said?
7 links, yes.
How many joints?
I don't know. Can I ask this question before I answer that?
Go ahead.
Alright, so you see the slider that's right there?
Yes,
See
yes.
how it's connected to 2 links? Oh, it's 3 links in total at one point. When it's 3 links in total to one point, isn't it two joints?
One joint is between this link and a slider.
Yeah.
It's making rotational possible.
Oh, okay.
And the other one is between the slider and this big guy.
Okay.
It's making translational.
Oh, okay.
So
Alright,
you can see 2 joints here, but it's between 3 different links.
Okay, so then I say 6 for the joints.
6 joints.
Yeah.
So 7 and 6. True. This is what you are.
Something like
Okay.
that.
Different out.
6 links, 6 joints, and 1 half joint.
6 links, 6 joints, and 1 half.
It's 6 links and 7 full joints.
6 links and 7 and 0. Okay, let's count. Just think about the meaning of links. It's a rigid body with at least 2 nodes which can be connected to the other links. So 1 is always the first link. So from O4 to B, it's a rigid body. Entire of this link is a rigid body. These 2 nodes, so I should count it at 1 link. Let me count this first one. O2 to A, it's a rigid body with 2 nodes at least. It's number 2. From B to O4, it's going to be 3. Slider. The slider has 1 joint which can be connected to link 2, and it has another joint which makes the relative translation of between motion between slider, which is itself, and link O4B. So I should count it at 1, number 4. Number 5, from B to C, these 2 joints, and 6 is the slider. So 6 is the right one for the number of links. Joints, 1 rotational, another rotational, 1 rotational here, 1 translational between slider and this guy. Number 5, number 6, rotational, 7 is sliding between ground and link 6. So 7 and 0. 6, 7, and 0. So degraph freedom would be 3 times 6 minus 1 minus 2 times 7. 15 minus 14 equals to 1.
So is that not a half joint?
This one, this is a slider. through this slider. If you remember, I said in the class, I count the slider as an individual link with two joints. One joint making rotational between the slider and the other link. I count it as number 3. And the other joint would be making translational motion between the slider and the other link, which is link number 3. So I count it as a 2 joint and 1 link. Any question on this? So far, okay. Let me draw this one more time here. So I'm ready to form the vectors. Each link should be treated as a vector. I assume O2 is the origin, so I will start from this. For this link, I put the arrow at this end. From O4 to this point, I put the arrow at this end. For this link, I put the arrow at this length. So we had how many links? 6. We had 6 links, 5 moving, one of them is ground. Out of 5, 3 of them rotational. And 2 slider. So from here to here also I put the arrow because I need it to form the vector loop. You will see why. So now, so first step, find the graph with them. Second step, form the vectors, just vectors. After you form the vector, you can label the angle. I have 3 rotational, so I have to have 3 angles. I should define 3 angles because 3 links are rotating. I will start from link 2. At this end, at this starting point, I label theta 2. Theta 2. Theta 2 because I found it as link number 2. For this link, from here to here, I label this angle at this end at the starting point of the vector. It's theta 3. I label this as theta 3. Yes.
Because vectors are from 4 to the top.
Yes.
They like it's 2 vectors I see.
This vector and this one.
There's 2 separate
This one, no, this is the vector that I formed. You will see I'm gonna use this vector to do the vector loop for this mechanism. But yes.
So like if it's on the left side, you draw the arrow going from like inside to the link, and if it's on the right side, it goes to the outside.
You are free to choose any. You are asking about forming the vectors or the angles. Right. You will start from the starting point of the vector, and it's starting from the ground, go all the way counterclockwise up to touch the link. Make sense? And for this one, this is the starting point. I should start from the ground up to that link. Theta 3, theta 2. For this one, this is link number 5. I should measure at this point of the link, starting from ground all the way theta 5. There is no theta 6 because it's for a slider. There is no theta 4 because it's for a slider. If I call this length as A, from here to here. Let me lay the this. This is point A. From point O4 to A, I will label as a B. From point A to point B, I label as C. I label this as D. Why do I have B? Because it's showing the location of the slider. From O4 to point A. It's location of the slider. And the remaining I will call C.
You call that whole thing because it's a fixed distance from O4 to B?
Yes, B plus C is constant. B plus C is not varying. Everybody can see O4 and B. This length cannot change, but B and C can vary when the mechanism is moved. So for this slider, the location is varying. So this is going to be S, and this offset is not changing. I label as E.
Excuse me.
Yes.
What theta 4 is that?
Theta. Okay. Theta 4. The slider doesn't have any angle.
Oh, that's theta 4. Okay.
But we don't have any theta 4. So theta 3. You see, we have 3 rotation around 2 slider, meaning 3 angles, 2 distance.
Oh, okay.
The distances are B and S. B and S. The angles are theta 3, theta 2, and theta 5. Any question before we move on? All right, constant. Whatever is not changing is constant. A is not changing. B is changing. C is changing. But B plus C is not varying. S is changing. D is not changing. And E is not varying. It's an offset. The variables are theta 3, theta 2, theta 3, theta 5, B or C, because if B is given, we can find C. B or C would be variable. They are not dependent. They are dependent. They are not independent. And S would be the last one. 1, 2, 3, 4, 5. Nouns would be constants. Plus degree of freedom is 1. One of them should be given. I assume theta 2 is given. We would like to do displacement analysis when the input link, which is link 2, is at the angle of theta 2. So we are solving for theta 3, theta 5, B or C, and S. Can you tell me how many loops do we need? We see 1, 2, 3, 4. 4 unknowns. Each loop can give us 2 equations. So if I need to solve for 4 unknowns, I need 4 equations. 4 equations. If you remember, meaning we need 2 loops. Now we are gonna. Yes.
What's BCC?
B or C. I mean that if these variables, B and C are dependent to each other. So don't count twice as a independent value, unknown. So I need 2 loops because we have 4 unknowns. The first loop must have theta 2 on that because it's a non-term that we have. So the first loop that I form is this guy. O2, A, O4, O4, O2. So loop 1. Loop 1 must have theta 2, so it's going to be O2A, A to O4, O4 to O2, just forming the loop. Second loop just look at this. O4B, don't have C. O4B, B to C, C to D, and D to O4. It's an offset slider crank. Second loop is an offset slider crank. O4B, B to C, C to D, and back to O4. So again, we should start with the loop which has the input angle or the whatever is the angle or variable which is now. Then form the second loop. So for the first loop, I'm writing the vector loop equation. Loop 1. First loop, point A is the point with two arrows ending to that. It's gonna be O to A start equals to O to O4 plus O4A. So this distance is constant. I forgot to label that. I labeled with F. So on loop 1, write the X component. X component for O to A is whatever is the length of this vector times the cosine of the angle. Length is A, cosine of theta 2 equals to O to O4. O to O4, the angle is 270. 270. So F cosine of 270. Or you can see it's going to be 0. There is no X component. This, I'm just writing that too. We go clockwise. From here, if I want to move counterclockwise, it's gonna be like this. 270. If you go in this way, it's gonna make a problem for the y component. You get positive number, but it should be negative. O4A, O4A. This length is B, cosine of theta 3.
Wait, what's the 270?
The angle of link vector, vector O4, O to O4 with the ground. This is O to O4, from O2 to O4. What is the angle of this vector? Starting from ground, going all the way counterclockwise until you touch the link. This angle is fixed, it's 270 degrees. Y component A sine of theta 2 equals to F sine of 270 plus B sine of theta 3. Let me just simplify these equations. A cosine of theta 2, this is 0, B cosine of theta 3, A sine of theta 2 equals to sine of 270 is negative, so negative 1. Negative 1 times F, negative F plus B sine of theta 3. Two unknowns. B and theta 3. B and theta 3 are not. I'm eliminating the theta 3 first, solve for B, back to this two equation to find theta 3. So B cosine of theta 3 equals to A cosine of theta 2. I should move this to the other side, it's going to be positive. Now I squared both sides. Add them up. If I square this, it's going to be b squared cosine squared plus d squared sine squared. It's going to be b squared. A squared cosine square of theta 2 plus this, I expanding this square sine. So a cosine square plus a square sine square is going to be a square plus f square plus 2af sine of theta 2. So b would be, we are solving for b, one of our variables. S square root of a square plus f square plus 2af sine of theta 2. A is down, F is down, theta 2 is given, you can solve for B. Back here, cosine of theta 3 will be A over B cosine of theta 2 divided by, not divided. B is given, find two values for theta 3. For sine of theta 3, you will find F plus A cosine of theta 2 divided by B. Find two values there, compare them, you will find the matching pair. Any question so far? So I will find theta 3 and B. So 2 out of 4, theta 3 and B. Now you have C because B plus C is given. You would have C if you want. We are not looking for that one. See now, I am looking for S and theta 5. So now second loop. Second loop is the offset slider crime. Offset slider crime, the input angle is theta 3 and the rest would be you know how to do displacement analysis for an offset slider crime. The input angle is theta 3 is coming from here. The loop is going to be this equals to S plus this vector plus CB. Make sense? The second loop. Second loop, loop 2 is offset slider crime. With input angle of theta 3. Solve for S and theta 5. Any question on this? First loop, always the best way is writing the vector loop equation and derive x component and y component. But if you look at in this triangle, if you are looking for b in this triangle, we can write the cosine rule. b squared would be a squared plus f squared minus 2af cosine of this angle. This angle is theta 2 plus 90. Cosine of that is going to be negative sine. You end up with this one. So on Wednesday, we are going to look at this mechanism. This one was the exam problem. I asked the students to do this question analysis for this one. We work on this. So we continue on Wednesday.